Imagine a spacecraft drifting far beyond Earth, somewhere in the deep silence between the stars. Suddenly, the signal disappears. No message, no rescue, no repair crew, no station nearby, and no chance to simply turn around and come home. But the terrifying part is this. The ship would not explode instantly, like it does in the movies. The lights might still be on. The computers might still be running. The navigation system might still be trying to keep the vessel on course. From the outside, it might even look alive. But from that moment on, an invisible countdown has already begun. Deep space does not need to destroy a ship in one violent attack. It only needs to wait. So how long could a real spacecraft survive out there? A few years? A few decades? 200 years? Maybe even 500? The real answer depends on one important question. Are we talking about a living spacecraft, or just a dead metal shell drifting through the dark? Because those are two very different things. A living spacecraft needs power. It needs guidance. It needs communication. It needs heating. It needs sensors. And if humans are on board, it also needs oxygen, water, food, medicine, waste recycling, and a stable environment. A dead spacecraft is different. Its body may drift for thousands, maybe even millions of years, but it can no longer think, move, speak, repair itself, or keep anyone alive. And the death of a spacecraft usually does not begin with the hull breaking apart. It begins with small things: tiny seals, pressure valves, joints, gaskets, electrical contacts, materials that looked perfectly strong when the ship first launched. In deep space, every sealed connection becomes a possible leak point. At first, that leak may be so small that it barely matters. But if the ship has to survive 10 years, 30 years, or 100 years, even a tiny flaw can become a fatal weakness. The ship heats up when it faces sunlight or radiation, then cools down again when it moves into darkness. Over and over, materials expand and contract. Metal stretches by microscopic amounts. Seals harden. Polymers become brittle. Small cracks begin to form. And in space, a small crack does not heal itself. It waits. It grows. And eventually, it becomes a problem the ship can no longer ignore. But even that is not the most dangerous threat. Deep space is not truly empty. It contains dust, hydrogen atoms, and tiny particles too small for the human eye to see. At normal speeds, they would be almost harmless. But an interstellar spacecraft cannot travel at normal speeds. If it wants to reach another star within a useful amount of time, it may need to move at 10, 15, or even 20% of the speed of light. At that kind of velocity, everything changes. A speck of dust that would mean nothing on Earth can hit the front of the spacecraft like a bullet. It does not need to be large. It only needs to be fast. That is why a serious Starship would need a shield at the front. Not a perfect shield, but a sacrificial one. A layer designed to slowly wear away, so the main body of the ship can survive behind it. After 10 years, that shield may be thinner. After 50 years, it may have lost a serious amount of material. And if the ship hits a larger dust grain that no one expected, the entire mission could be in danger. This is one of the cruelest problems in interstellar travel. The faster you go, the sooner you arrive, but the more violent every impact becomes. Slow down, and the dust becomes less deadly. But the voyage takes longer, which gives every other system more time to fail. Space offers no easy choices. And even if the ship survives the dust, another enemy is attacking it every second: cosmic radiation. Radiation does not only threaten human bodies, it attacks electronics. It corrupts memory. It damages sensors. It slowly weakens materials. A single energetic particle can strike a computer chip and flip one bit of data. That may sound tiny, but on a spacecraft, billions or even trillions of miles from Earth, a small error in navigation, power control, or life support can become a disaster. Radiation can make the cameras noisy. It can damage star trackers. It can interfere with stored data. It can slowly make metals and other materials more brittle over time. In other words, radiation does not need to rip the ship apart. It only needs to make the ship confused. And in deep space, a confused spacecraft is already dying. But if we had to choose the single most important thing that decides whether a spacecraft is still alive, it would not be the hull. It would be power. Power is the heart of the ship. Without power, the computers die. Without power, the heaters shut down. Without power, communication disappears. Without power, the sensors go blind. Without power, repair robots become useless statues. If the spacecraft only had batteries or a weak backup system, it might last only months or a few years. If it used a nuclear power source, similar in spirit to deep space probes, it might last for decades, maybe 30 years, maybe 40, maybe 60 in a strong scenario. But power does not usually vanish all at once. It fades. At first, everything still works. Then the ship begins to make sacrifices. It shuts down non-essential systems. It turns off extra cameras. It reduces sensor activity. It cuts heating to less important areas. It communicates less often. It keeps only the most critical systems alive. The spacecraft does not die with a single explosion. It dies by turning itself off, piece by piece. And if humans are on board, everything becomes far more difficult. A robotic probe only needs to keep machines alive. A crewed spacecraft has to keep an entire tiny world alive. Humans need oxygen. They need clean water. They need food. They need stable temperature. They need medicine. They need waste processing. They need light. They need sleep. They need psychological stability. They need a reason to keep going. Inside a metal structure, surrounded by endless darkness. If the air recycling system fails, carbon dioxide can build up. If the water recovery system breaks, the crew begins losing one of its most precious resources. If the food production system fails, the future of the mission begins to shrink. If the heating system weakens, parts of the ship can become too cold to support life. On a crewed spacecraft, the most fragile component is not the engine. It is not the shield. It is not even the computer. The most fragile component is the human being. That is why the first true interstellar missions will probably not carry people. They will likely be small robotic probes, because robots do not need air, water, food, sleep, or hope. A well-designed robotic spacecraft with strong power, radiation-hardened electronics, durable materials, and some ability to repair itself could possibly remain functional for 100 to 200 years in an ambitious future scenario. But 500 years is a very different story. A spacecraft that survives for 5 centuries cannot just be a vehicle. It has to be a factory. It needs repair robots. It needs raw materials. It needs 3D printers. It needs spare parts. It needs chemical systems. It needs recycling systems. It needs the ability to replace pumps, valves, wires, sensors, and shielding panels, and even the robots that do the repairs. Because here's the strange problem. The robots that repair the ship can also break down. So who repairs the repair robots? To survive for centuries, a starship needs more than spare parts. It needs a maintenance chain that can maintain itself. A true interstellar spacecraft would not be like a car, a plane, or even a space station. It would be closer to a small industrial city, traveling between the stars. It would have to inspect itself, repair itself, recycle itself, and decide which systems must be sacrificed so the mission can continue. If power starts running low, the ship may have to choose between communication and heating, between cameras and navigation, between scientific instruments and core computers. Every choice would be like losing part of its own body just to keep the rest alive. So how long could a spacecraft really survive in deep space? If it is small and has limited power, maybe only months to a few years. If it is a deep space probe built with durable technology, it may survive for several decades, perhaps 30 to 60 years under good conditions. If it is a future robotic Starship, designed with extreme redundancy and self-repair, 100 to 200 years becomes an imaginable target. But a crew generation ship surviving 500 years is not just an engineering problem. It is the problem of building a civilization in miniature. It must preserve human life. It must preserve knowledge. It must preserve machinery. It must preserve order. And it must preserve belief in a destination that no one on board may ever personally see. But one thing is almost certain: the body of the ship can outlive almost everything inside it. After the power is gone, after the computers are silent, after the last signal has vanished, the hull may still continue drifting. There is no rain to rust it, no wind to erode it, no bacteria to consume it, no ground for it to fall onto. It could drift for thousands of years, maybe millions, but by then, it would no longer be a living spacecraft. It would be a metal ghost, carrying the final memory of the mission that created it. So the real answer is not one simple number. A spacecraft might survive a few years, a few decades, 100 years, 200 years, and in an extremely ambitious future, maybe 500 years, but never forever. Because out there, everything is working against it. Dust wears down the shield. Radiation corrupts electronics. Power slowly fades. Machines wear out. Seals crack. Data decays. And every system grows older in silence. Space does not need to be angry. Space does not need to attack. Space only needs time. The real question is not whether a spacecraft can last forever. It cannot. The real question is whether we can build one, strong enough, smart enough, and stubborn enough to keep winning thousands of small battles, long enough to finish the journey. A true Starship would not survive because it is perfect. It would survive because it expects failure. It would be designed to break in small ways, repair itself quickly, and keep moving before the universe can wear it down completely. That is the real secret of surviving deep space. Not magic, not science fiction, just power, materials, redundancy, repair, and patient engineering. So if someone asks how long a spacecraft can survive beyond Earth, the most honest answer is this: long enough if we build it carefully enough, but never forever. Because in deep space, time is the final enemy. And every spacecraft we send into the darkness is really making the same quiet promise to keep going for as long as it possibly can. If you enjoyed this journey into the engineering reality of deep space, subscribe to Cosmic Theory Lab for more strange, silent, and terrifying questions waiting beyond our world. See you in the next episode.